All right. Good afternoon, everybody. Hopefully, you had a nice weekend. So, I guess for today, we'll just sort of continue on content from last week. So, we first talked about our first sort of non-comparison sorting algorithm. So remember we talked about the comparison models and what's their lower bounds. So remember for a comparison-based sorting, you cannot do better than n log n in the worst case. So there are cases where you can get better than n log n. So for example, insertion sort can get O of n in the best case, but that proof I went over last time just suggests that in the worst case, you cannot do better than n log n. We discussed bucket sort, which was our first non-comparison sorting algorithm, which has some good, sort of runtimes for it. So let's go to the screen share and just sort of recap that a little bit, and then we can go on to new materials. So let's start screen share. There it is. Alrighty. So with bucket sort, it was really the very simplest non-comparison sort of sorting algorithm. So we have this array A, where it's not sorted, obviously. We want to sort this. So this example is from the book. And the way you do this is, of course, you just first find the biggest number in this list and compute how many digits this number is. So take log base of whatever base you're using of that number. That'll give you how many digits that number is. You divide it by that number. So what you do is every single, so this case here for this example, the biggest number is 94 with 2 digits. So then you divide every number of, so divide it by 10 to the power 2 in this case, every number. So if you want to map, let's say 78 into this B array, which is your buckets essentially here, you take 78 divided by 100, multiply it by 10, and then take the floor of that, which gives you 7. So 78 goes into bucket index 7. For 17, it was 17 divided by 100 to get 0.17. Multiply it by 10 because you have 10 buckets here, which gives you 1.7. The floor of that will give you 1. You insert it there, and same for the rest of these. So basically, you just take every index in your, every element in your array, divide it by the base up to the number of digits. In this case, we have base 10, and the biggest number has 2 digits. So take each number, divide it by 10 to the power 2, multiply it by number of buckets. Number of buckets will always equal the amount of elements in your array. So that's kind of why bucket sort is kind of nice, because this way it's very unlikely to have too many elements in one location. So what you do is, after you have these elements inserted, it's going to be an array of linked lists. You sort them using a regular sorting algorithm. So we usually just use insertion sort because it works pretty nicely on small size lists, because each bucket will have small amount of elements in it. And then after that, we have them sorted just like this. We just go ahead and now concatenate. So we go from top to bottom. We insert 12 into the array, then 17, then 21, then 23, and 26, and so forth. And there'll be one sorted array. So the whole idea with this algorithm is that, well, since we have n buckets and n elements, it's very unlikely to have each bucket contain too many elements. So we're going to have a very small size for each bucket. So using insertion sort on each bucket is going to be relatively constant if you have, 4 or 5 elements at most in each bucket. So there is statistics done on this where if you have, let's say, 100 elements or larger, as the size grows, then the most number of elements each bucket will contain will be around roughly 5, statistically speaking. So that means that each bucket to sort will be pretty quick. So in the worst case, obviously, you could have your numbers very much not nicely distributed, where you have, let's say, for example, you have a lot of numbers and they're all in the tens, for example, from 10 to 19. So each one bucket will contain all the elements. You have to do that one insertion sort of all the elements, which will be n squared in that case. But that's in a very extreme situation. So the average case scenario, that's not going to happen. Typically, the numbers will be nicely distributed among the buckets, and you'll not have too many elements in each bucket. So it'll be very fast for each one of them, and then concatenating them is linear times. So it'll be O of n in the average case, essentially. So that's our first algorithm we've covered. So now let's go ahead and talk about a different how shall we say, different non-comparison model. So let's go ahead and go over to OneNote and create a new page. So we'll go over our next one, counting sort. So that's going to be our next sort of non-comparison sorting algorithm. So I'll put that here as well. It's a non-comparison sorting algorithm. So just to repeat what that means, the idea is that we will never compare between two elements in our array. So for every other comparison-based sorting, we always compare elements in the array. This will, again, we're not going to compare between two elements in our array. That's the whole idea with the non-comparison model. So what we have to do in this algorithm, first, you have to find sort of k, which is the largest element in the array. Or we want to find really the range, essentially. So you want to find the range from smallest to largest elements in the array. However, in the worst case, I guess, it'll be from 0 to k will be sort of the range. So the smallest one will be 0, and the biggest one will be k, typically. But either way, we want to find that range, essentially. So this part, I guess, does require some comparison, I suppose, to find the largest. But this part's doing comparisons. But after this, though, then we don't do any more comparisons at this point. So what's going to happen now is in this algorithm, we're going to have our given array. So given an array, I'll call it A, of size n. Of course, you first, I guess I should have had these notes flipped, or these two bullets here. But we first have the array, we find that k value, but I'll just go ahead and just assume that once we have our array A, we can find our range, basically. So given the array A of size m, we're going to then allocate an array of size, we're going to allocate an array B, no, array C, my mistake, array C of size k. So basically, the array A, so this is actually, again, I'm using the example from the book. So in the A array, we're gonna have the following ranges. I'll put this above. It's gonna go from 1 to n, not from 0 to n minus 1. And then for our C array, it's going to range from 0 up to k will be the range. So actually, it's going to be size k plus 1 in reality then. So I'll just put that here, size k plus 1. And then, we're going to have another array B, which is going to be of size n. So we're going to allocate an array B of size n, which the ranges, of course, will go from 1 to n. So this B array is going to be your final product. And A was your original array. And C is going to be that array that's going to help counting sort complete its task. So that's sort of, we first have to, given our array A, we first have to find the range. So in our array, we want to find the biggest value. So typically, our range will be from 0 to k, but it could be sort of from some smallest value to the biggest value. Find that range, essentially. But we'll just assume that 0 will be our first element, our smallest, and k will be our biggest, just to make things easier. And then we're going to have another array B of size n from 1 to n indices, like that. So this is actually the same idea from the book. And once we have all these arrays set up, and we found our k value, we can now begin the algorithm. Let's go over the pseudocode of the algorithm. Pseudocode for sort. So we're going to have is the following. So we're going to first have our loop here. So for I equals 0 to k, we're going to set every element in C with the value 0. So first, this C array is going to really count how many instances of every element we have in our original array. So we're sort of doing a hash almost in a sense. We're going to count every element in the array and how many occurrences of the element exist in the array. But we'll do the example, then it'll make more sense, but I'll just say it right there. And then we do the following loop right here. So for j equals 1 to n, we're going to have C at index A of j equals C A of j plus 1. So we're just sort of mapping elements from the array, our original given array, into C. We're trying to count how many occurrences of each element in our original array A. So C will first maintain that. That's what this loop right there is essentially doing. And I'll put this dot above the J, I guess, so it makes more sense. Anyway, so that's the idea really there. So now that we have that, now we have this other loop over here, which I'll explain this in a second. I'll first write this out. So for, I guess they use I again in the book. So for I equals 1 to k, actually it should be really from 0 to k, my mistake. Yeah, from 0 to k. Yeah, I wrote that down wrong possibly. And we're going to have C index I equals C index I plus C I minus 1. So what this loop really does is that it's going to really compute where the elements have to go in a potential B array. Kind of hard to explain this, but I guess when we draw the example out, I'll sort of go back to this. But really, that's what this loop is really doing essentially, trying to find out where the elements are going to go. Because you want to have like these range of how many instances of an element exist and find the location. But you know what, I'll just go ahead and I'll explain that once we do the algorithm. And the last part here is we're going to actually going to do this sorting loop. So we're going to have, I guess I use j again in the book. So for j equals n to 1, so we're going from right to left in this loop, we're going to have this B array at index C. I think this means one more bracket, yeah, equals A index J. So we're going to, this is going to be where we actually are sorting the array. We're going to find a location of where, so we have A of J. We're trying to find where that element has to go into the sorted array. So this B array is going to be your final sorted array. So we want to locate where in this B array does A, J have to go. So you first have to look into our C array to see which index it's supposed to go to, and we're going to locate that index and map that to this B array. It's kind of weird, but I think the example will make much more sense. And then of course we had the second part, so both be inside the same loop, these two statements. So then we do this at the end. Okay, yeah, I remember this now. So the purpose of doing this portion is that after we map an element to this B array, we want to subtract it by 1 because now if another instance of an element exists, it's going to appear to the left of the last one. So let's say we had 2 3s. The first 3 would go to this index over here in the sorted array, but another 3 appears, well, it has to appear to the left of the last 3. Yeah, we'll do an example on that, but that's really, this is a pseudocode really for how it works. So it's really not so hard. And you can see here, there's no comparisons being done. The only comparison we do really is trying to find that range, or we look for that biggest element k, And we say you want to find the range of smallest to biggest element in the list and have to allocate this C array of size k. That part requires some comparisons to find that min and max element. But after that, this sorting loop here, there's no real comparisons. You're doing a bunch of sort of like a hash mechanism again, which is not doing a comparison. You just sort of go to element, look it up, and do some work on that. So that's basically what's happening here. Here's our pseudocode. So I think now having an example that covers this will be much more useful than just me just talking and rambling more on this pseudocode. So I'm going to go ahead and pull out the example so I can just just so I can go over it, so I don't make a mistake with it. Let's do an example next. So we're first given our array, so I'm going to create a box over here. Hopefully OneNote does correctly make a box out of this using from handwriting to box. Huh, look at that. So at this point now, we're going to have an 8 size array. So let's see, we're going to have this many elements. So that should be 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, perfect. So again, this example is from the book, just to kind of go back in case if this doesn't make sense, then at least this will, at least you can kind of get an idea here. You can read the book, I suppose, if let's say this example in class doesn't really help you, but let's go ahead and put the array brackets over here. All right. And the elements we're going to be given will be 2, 5, 3, 0, 2, 3, 0, 3. So in this array, obviously, we can see that k is going to be 5. So 5 is the biggest element in this array. So we're going to have the C array is going to range from 0 to 5. So it'll be 6 elements for our C array. So I'll put this here. It's going to be our A array, so we can refer to that. That'll create our C array, but I'll probably zoom out so we can see the entire example in a bit. But I'm going to first just draw this C array. Awesome. And let's say we're going to have 6 elements. We need 5 lines, I believe. 6, perfect. And this is going to have the indices 0, 1, 2, 3, 4, and 5. So what happens now is that loop is going to basically set all these to 0. That was that one loop we had above. Every element in this C array, so I'll put this here as C. It's going to be all zeros initially. So remember that loop just sets them all to 0. Okay, so now we have to count every instance of the elements sort of from A in the C array. Okay, fine. So these indices of the C array is going to be really an index or an element, sorry, in this A array. So what you do first in that loop is you have to count every instance, in this case 2, the first element in our array A. So index 2 in this C array, we increment this by 1. I'll write this here to be like in, so let me write this in green. So we're going to have 1 now, because we took this element 2 in its A array, map it to index 2 of our C array, increment it by 1. So now we know that this A array contains 1 2 value. And then next element in the A array is going to be 5. So you go to index 5 of C, increment this by 1. So now we know we have 1 5 element in this A array. Next element contains the value 3. So you go to index 3 of our C array, increment this by 1. So we have 1, 3 in our A array. Now, next element in our A array contains 4. I guess I forgot to turn off Discord. All right. So next element, index 4 contains 0. So you go to index 0 to C array, increment this by 1. So all we're doing is sort of making this count. So Now, next element contains a value 2. Index 2 incremented by 1. So now we know we have two elements in this A array. Perfect. The next element in this array will be 3. So you go to index 3 of the C array, increment that by 1 to make it 2. So now we know we have 2 3s in our A array. The next element will contain 0. Go to index 0 of C, increment that by 1 as well, and that's going to tell us that we have 2 zeros in our A array. And the last element in our A array will be 3. We go to index 3 of C array because we have to map it, so A of J, which is 3, go to index 3 of a C array, add it by 1. So now we're done. So essentially, in our A array, we know we have 2 zeros, we have no 1s, we have 2 2s, we have 3 3s, no 4s, and we have 1 5. So the index of C really tells us each element in our A array. It tells us how many of each element we have. So we have that part so far done. Okay, so that's the first step. And now here comes a very weird, confusing third loop, I suppose, in our counting sort. So remember, we first had to set all of the C's to 0. This part right here, the second loop was what we just did. We just sort of mapped every element from A to C array and counted how many instances we had. Now we have to do this third loop, which is going to basically add the previous size over to the next one. So we're just taking C of I plus C of I minus 1, adding together, and storing the C of I. So let's go ahead and just run this loop and see what this does. So I'm going to basically, I'll copy this, I'll have to redraw this entire block here. I'll try to copy this. Okay, so that worked out. So I'm gonna go ahead and just write this over here. So we have 2 in this location, 0. We have 2 over here. Wait, still, we have 3 in this location. And we have, I probably can't erase that small. Maybe I can. Hold on, try to really carefully try to erase that. Perfect. Let me just go back to the way it was. Almost. And then for 5, we had 1. That's our current array. Our C array currently contains these elements. So now what we have to do is just literally go ahead and say, well, I'm going to take index 1, add it by index 0. So 2 plus 0, I'm going to write 2 into this location. And then index 2, we're going to take whatever is in index 2, which is 2, plus index 1, which will give us 4. And then index 3, which is 3, plus the previous one is 4. We'll get a total of 7 stored here. And then index 4 will contain 0 plus 7. 7 right there. An element to index 5 is a 1 plus the previous one, 7, will be 8. And we assign 8 over there. So that's basically what happens now. I guess that's basically the idea here. So now what this really tells us is that the first time we see a 5, it has to go to index 8. And then if we see a 4, we go to 7. If we see a 3, we go to index 7. So this tells us which elements, each element in an array has to go into that B array. So we'll go ahead and sort of now run this sort of the final loop, which is this one right here. So we just did this right now. This loop right here is going to now basically sort of complete our sort. Let's go ahead and run that. So we're going to have our B array at the very end, which is going to basically be the same size as the A array. So you can probably just copy and paste this. So I'll have to redraw this entire array. Then I'll zoom out so we can see everything, so we can actually do this out pretty simply. Let's go ahead and just put this here. This will be B, our final product. Now I'll clear these all out. Now zoom out so we can see everything. Hopefully you can kind of catch everything into one frame. think it's good. I think it's visible on the screen here. Well, I can see it, but hopefully you can see these on WebEx. It's not too zoomed out. Okay, so now going to our last loop, we're going to the first follow. We're going to start from our rightmost position, n, which is going to be 8. And we first take this value, which is going to be 3. So a of j will be 3. So we go to index 3 of our C array, because a of j contains 3. Go to index 3 of our C array. So C of 3 contains the value 3. So we're going to go ahead, oh, sorry, it contains 7. So we're going to use this array over here at the bottom. So this array here was kind of needed earlier, but I'll go ahead now and sort of box this in, boxed in right now, so denoting that we don't need this anymore. So not going to be used anymore. We just need this just for intermediate levels. So no longer needed. So focus only on that second C. This one right here was just needed temporarily to create this final C array. So we first have to go 3, a of j is 3, go to index 3 of C, which is going to be right there, contains 7. So the first instance of 3 has to go to index 7 of our B array. So 3 goes over here. That's where 3 is going to be in its final position. And after that, we have to decrement this by 1. So now we're going to decrement this to make this into a 6. And the purpose is, if we see another 3 again, it will go to index 6 this time, which makes sense, because if we have duplicates, they're going to be side by side with each other. So if we see a 3 again, it goes to just index 6 of our B array, which makes sense. So now, in our loop, we now have to go to our next element, which will be index 7, which will be a 0. We find, well, where does 0 have to go? Well, we take a of j, which is 0, go to C array, and C of 0 gives us 2. Which means that basically 0 has to index 2 of our B array, so 0 goes over here. Because it tells us exactly which index you want to put, so which element we want to have 0 go to. So the C tells us, well, 0 goes to index 2 in our B array. Then decrement this by 1. So if we have another 0 once again, that second instance of 0 would have to go to the left of the last 0, which is going to be index 1. So this C array only maintains where the elements are going to go at the end. So now, our next element will be 3. So element 3, let's find out where in the array it has to go. So 3, we go to index 3 of our C array, which gives us 6. That means 3 has to go to index 6, which makes sense. Which now we're going to decrement this down by 1, like that, 5. So I'm going to put it above actually, so we don't confuse it with anything else, like that. So if we see a 3 again, it would have to go to index 5 from now on. So let's go ahead and continue. So in our array, now we're looking at this value 2. So I want to go ahead and find where does 2 have to go into my final sorted array. So we have to go to index 2 of our C array, which gives us 4. So 2 is going to go to index 4. Then we decrement this by 1 at the end. So now if we do see a 2 again, it has to go to index 3 to the left of the last 2, which does, in fact, I think it does make sense. So now let's continue. Now our next element from right to left is going to be this value 0. Let's find out where does it have to go. So 0 is going to actually go to, well, let's go to index 0 of C, and it gives us the value 1, which means 0 has to go to index 1, which is right here. Decrement this down by 1 to make it a 0. So let's continue. So after this index, after this value 0, the next element to the left will be 3. I want to find where does 3 have to go. So I first go to into array C and go to index 3 because I'm looking at value 3 right there. Index 3 gives me the value 5, so I have to go index 5 of my B array and put 3 over here. And decrement this again by 1, make it now a 4. And then, well, let's continue. So A array, we looked at 3. So now let's look at the next element to the left of 3, which will be 5. So you have to find where does 5 have to go in our sorted array. So 5, well, it has, we go to the C array. So 5 has indexed 8. So if we go to looking at this 5 value, we have to go to index 5 in our C array and look at the value stored there, which is 8, which means go to index 8 of the B array. So 5 is going to go over here. And decrement this by 1. Like that. And then our last element, which will be a leftmost element, which is 2. Let's go to index 2 of our C array, which contains 3. So go to index 3 of our B array, which is going to be where we're going to write 2. And decrement this by 1 more. And there we have it. We have our sorted array. So all we had to do is keep on mapping things. You had to kind of, first map, let's say, value 3 to index 3 of a C array, because the value to map to the B array. So you had to kind of do a lot of mappings like that in order to find the location of where every element had to go. So basically here, okay, so this does work, and there's actually one sort of remark I want to make about counting sort, is that it's a stable sorting algorithm. Let's go ahead and write this over here. Oops. I'll zoom in on this first to write it nice, and I'll go back. So counting sort is a stable sorting algorithm. Now, what the heck does that even mean? I mean, the word stable really implies that it always works. Well, it's going to always work. I mean, there's no way this is not going to work. What does that mean to be stable? Well, it really means this. So, okay, if you look at, let's say, these 3 3s over here, let's just focus only on this. Look at just these 3 3s. So we did counting sort. We first took this 3 over here, and we mapped it into this position, into that index 7. Then as we moved from right to left, this second 3 that we saw, this one got mapped to this position, index 6. And then the third 3 we saw from right to left, this one ended up getting mapped to that position. So we see here that it's still sorted, but in our original array A, our last 3 is still the third 3 in this B array, if you notice this. So what happened was, so typically for sorting, having a stable sort does not really make a difference, to be honest, because really, I mean, let's say we have these 3 3s. Well, who cares what order they're in? Because let's say if let's say a third 3 was actually sort of swapped to the front, and the first 3 ended up getting swapped to the end, well, who cares? Because they're all 3s, it's still going to be sorted, correct? And typically, that is actually true. It doesn't really matter. But we just want to observe that this is, in fact, going to be a stable sort. So which means that this rightmost 3 in A is going to appear the rightmost among these 3 3s over here. And same thing for the 2 values. This index 5 2, so I can also do the same thing over here as well. I'll just erase this and talk about that as well, but that's what this means to be stable, actually. So I'll try to erase these circles. Let's look at the 2's, for example. So we had to go ahead and put this 2 into its correct position. This 2 ended up going over here. And then as we moved along, this second instance of we saw 2 from right to left, well, this 2 ended up going over here. So it's still in the same position. So even though it's not in the same position, the sorted array amongst themselves, that writer 2 is still to the right of that 2 that was on the left in the original array. That's what makes it a stable sorting algorithm. So typically it's not very important to really have a stable sort because most of the time, who cares? As long as it's still sorted. I mean, it doesn't really matter which two came first. I mean, they're both twos, right? But it's just, we want to observe that it is in fact a stable sorting algorithm. And sometimes it can make a difference, especially for maybe for sort of struct types or class types. If let's say we have a list of people's birthdays, and there's two people who both have the same sort of birthday, they're both 25 years old. But let's say this first person came first in the list, so you want to make sure maybe we wanted to have, let's say we have these two 25s, we want them to still stay in the same relative position amongst themselves for some reason. Let's say we have like, Bob is 25, Alice is 25, and Bob came first in the list. We want to still preserve that Bob will still come before Alice in the list. We still want to preserve that essentially. So that's what this stable sorting really means. And we'll go over in a second as to why it can be beneficial to have a stable sorting algorithm. But that's the idea of what it means to be a stable sorting algorithm. Okay, so I guess it's kind of, we can observe that, but it's sort of the idea. So any questions on counting sort at all? Alrighty, so let's now go over the runtime for counting sort, of course. As always, we have to go over runtime for any algorithm. Try this out. See if I can make it so the straight line gets drawn. No, didn't work. Okay, that's fine. So let's go over the time complexity. For counting sort. So basically, it depends really on the size k. So the runtime really is going to be this. So I'll just go ahead and just write the runtime out with theta n plus k. I'll just go ahead and talk about this right there. So basically, in every single instance, every loop, so let's go to the top and look at our source code. We have several loops. So this for loop will take n steps. This takes n steps as well, and these ones take k steps. So basically, whichever one is the bigger value kind of overshadows the algorithm, essentially. So in reality, we want k to be n or less, because size n is already a fixed size, if you will. So we're passing an array of size n into this function, or into this counting sort algorithm, so n is not going to get larger. N is passed in the size n list. So k, well, k can be pretty big. What if we're sorting really big numbers? I mean, this example right here, we get small numbers. Imagine if we had number 100. You would have 0 to 100 in that C array. It will take 100 steps, 101 steps to set them all to be 0. So that part would be kind of slow. Now, this part we map elements from A into that B array is pretty fast, but setting this C array is pretty slow. You can't really skip elements over because if you, let's say, we only preserve the elements in the C array, let's say the indices, we only preserve indices that are in the A array, well, then the problem is we have to have them kind of sorted. If we sort these by indices, then there's no point really doing a counting sort. So we have to have this big range. So if the range is very large, then C will be a very big array. And it will take k steps to set them, to clear them out, to make them all 0, because even in certain languages where if you allocate an array and it sets everything to 0, it's still going to, behind the scenes, it has to initialize everything to 0. There's no magic for that. I mean, I know maybe in Python it will automatically do it for you, but somebody is doing that for you. There's no way it will have zeros all magically assigned. So you have to allocate all the elements, k elements, and set them all to 0. But that takes k time to do. So the C array is the bottleneck for counting sorts. So depending on how big k is, determines the runtime of this sort. So the idea is um, if k equals O of n, so it's either size n or smaller, then counting sort is theta of n, which means it's going to be, if k is n, then n plus n is n. Or if k is less than n, just as good. So we have a restriction. If k is O of n, so it's going to be n size or smaller, then counting sort is definitely going to be linear. So it's nice, but it's kind of restrictive because, well, what if k is pretty big? What if k is much bigger than n? Well, then runtime is going to be whatever k is. Let's say if k equals to n squared. Well, then it's n squared runtime. So k is that bottleneck. So this is a pretty good algorithm. The problem is that, well, we're dependent too much on k. Now, if k could be a pretty big value, let's say if k could be a polynomial of n and still be linear, that would be great, but unfortunately, no. K has to be no more than n in size. So a range can't be too large, basically. So a C array can't be too large, or else we get a worse runtime than n. So, okay, so we have this basically this counting sort introduced, which is theta of n, but only in some instances. What if we can find maybe something better that does use counting sort, but its k value is not going to be so restricted, because right now it is restricted where k has to be n or less. So that's not really very typical scenario. It's very easy to have a case where k can be pretty large. So really, this is really best case theta of n, but average case though, not really, because k is very easily can be large, and there's no way to, like for bucket sort, it's very hard to get that n squared runtime. But for this, it's pretty simple to have it where k is bigger, and we can have a sort three numbers that are, we have, let's say I want to sort 0, 50, and 1000. Well, there you go. I just found a simple example right there where counting sort will be worse than n. So very simple to find an instance like that. So let's go ahead now and discuss maybe another comparison-based sorting algorithm that maybe is not as restrictive as counting sort. So let's go ahead and discuss that next. Radix sort. This will be our last non-comparison based sorting algorithm. Let's go ahead and sort of define this. So it's again another non-comparison based sorting algorithm. So once again, we're not going to really compare between two elements. Now, of course, in counting sort, we have to find that biggest k value, but after that, though, it's all just sort of mapping things around until we finally find that location for where the element has to go into that sorted array. But basically, there's not much comparison going on. So same idea with radix sort, there's no comparison. So essentially, what's going to happen is, so we use a stable sorting algorithm to sort the elements by digit. From the from the least significant digit to the most. Is that how it is, or the most? I think it's how it's written. Most significant digit. And it must be a stable sort. So we have to have a stable sort for this to work. And I'll explain once we go over the example as to why, but it must be stable sort. So here's an example right now where it's very preferable to have a stable sorting algorithm. So you want to make sure that if you have elements in a certain order, when we sort them, we want to make sure that they're still that same relative order in which they once were. So if you have, let's say, 2 3s, I want to make sure that the writer 3 is still to the right of that lefter 3 in that original array. That's probably very bad grammar, but you get the idea. The writer, so the 3 to the right of the other 3. So we want to make sure we still preserve that same order if duplicates exist in the array. So a stable sort must be used, or else it won't actually work. We'll show an example as to why this could mess up, but once we go over the example. So now, what happens here is we perform the amount of passes of counting sort, because we know counting sort is a stable sort, so we're going to use counting sort. We're going to do this the amount of times. And then, of course, the denotes the amount of digits in the largest element. The largest element in the list. So all we have to do is do this d amount of passes. So we're going to essentially first run a pass where we sort all the elements from the rightmost digit, or least significant digit, up to the most significant digit. That's basically what's going on. So for counting sort, so each pass of counting sort takes theta n plus, use b. So we used k before, now we're going to use b, where b is the base of the numbers. So if we're sorting base 10 numbers, then we're going to have our C array will have 10 elements because there's at most 10 digits. If you're using binary, then we're only going to have 2 because B will be 2 in that case. If you're using hexadecimal, B will be 16. So based on the base representation of the numbers. So we'll use base 10. That's kind of more typical, I suppose. So you have to do this counting sort. We're going to do each pass will be n plus b. And we're going to do this d number of times. So radix sort has a runtime of theta d times n plus b. And we'll go over more analysis of that after we cover the example, but really, n plus b is a runtime for counting sort. Runtime for each pass of counting sort. And we have to do this counting sort d number of times for every digit. From the rightmost to the leftmost, we do counting sort that many times. We always sort them by each digit. If you do this, it will produce a sorted list. So we'll go over the actual more analysis of the runtime in a second, but that really is the runtime because each digit there can't be more than b of them. Or in this case, if we have a base 10 representation, each digit, there can't be more than 10 of them. So we can definitely allocate a C array of size 10 every single time, which is actually kind of nice. So hopefully this will give us a good runtime or better expected runtime, because counting sort really, it's sort of, in a sense, is based really on the size of the array. So it's really O of k in a sense, really, to think about it, or theta of k, because it depends on the biggest number, because typically it's very simple to have cases where it's larger than n. But anyway, let's go ahead now and do an example of radix sort. This will take a little time, but we can, of course, talk about this. And then we'll go over the runtime analysis of Radix Sort. Let's do an example. It's going to be kind of a pain to do all this, but that's just, let's get to it. So here's original array will be given. So again, I think we're given the same array, so the same example from the book again, just to kind of make things sort of easier. Just so you can read the book if in case this presentation doesn't make sense. So we'll have, again, we'll have index 1, index 2, index 3. So I'm probably going to copy and paste this several times to sort of reduce, to sort of speed up the example. But I'll have to also copy the C array a couple of times as well. So first have just our A array, and we'll have 329, 457, 657, 839, 436, 720, and 355. So obviously this array is not sorted, so you have to, of course, sort this array. So the first step is we're going to sort these by their rightmost digit. That's our first step, because for Radix Sort, we're going to sort the elements by that rightmost digit. Okay, so we're going to have a C array created. I'll just go ahead and I'll try to speed this up if I can. So we're going to have 10 elements here. So this will be our C array. I'll probably condense this a little bit. I can probably copy and paste both these images for every example. So this will definitely speed up this example. Kind of one of the benefits of using OneNote in class instead of the classical whiteboarding class. So of course, we're going to set all the elements in C to be 0, as always. I'll kind of speed this example up, so it's not going to be good for note-taking, but I guess the video will help you with this one. So we're going to first count every digit. So the first digit, we have a 9. We're going to increment that by 1. So we have 1 9-digit seen so far. The next element, index 2, contains that 7. We're going to add 1 to this, so we're counting how many digits we've seen so far. The next element is 657, contains a 7 for its rightmost digit, so we increment this by 1 to make it 2. Then we have 839, so it has 9 for its rightmost digit, so increment that by 1 as well. Then we see a 6, index 6 of this array, increment this by 1. Then we have a 0, go to index 0 of our C array, increment that by 1. And then the last one, 5, go to index 5 in our array, increment this by 1. Let me make sure I get this correct. So 1, 2, 3, 5, 7. Okay, so we have all numbers accounted for. So now for counting, sort of what happens next is, remember, we have to basically add everything over. So I guess I'll do this in the following fashion. So we're going to basically rewrite this to become a 1. So remember, we add them over. This becomes 2, 3, then 5, then 5, then 7. Make sure my notes are correct with this. I believe they are correct. Okay, cool. So anyway, now we have to get this sorted into our B array. So I'm going to actually just copy this, because it's going to be the same size as the A array, of course. So I'll copy this over here. This will be our B array. Oops. Now erase all of these. Let's go ahead and run counting sort by only having just these rightmost digits. included. Let me zoom out so we can see the entire, you can see all of this. Okay, perfect. So starting from the rightmost position for A array, J55, has a value 5 for its rightmost position. So we jump to index 5 of our C array, and it contains a value 2. So we're going to put 355 into index 2. And we're going to decrement this by 1 to make it now it's going to be 1. Alrighty, now let's go ahead and go to the next element to the left. So we have 720. It contains 0 for its rightmost digit. So we go to index 0 of our C array, and it contains 1. So we're going to write 720 into index 1, decrement this by 1, just like that. And as we continue, we have 436. We're going to sort of go to index 6 of our C array, contains 3. So 436 would go over here and decrement this by 1. Then 839 contains a 9 for its rightmost digit. Index 9 contains the value 7. So we're going to put 839 into index 7 and decrement this by 1, just like that. And then 657, we're going to find where it locates. So it contains 7 for its rightmost digit. Index 7 of the C array contains 5. So we're going to write this value into index 5. And then we're going to decrement this down by 1 to make it 6. And then 457 has 7 for its rightmost digit. So index 7 of our C array contains 6. We put that 457 right there and decrement that 7 by 1, make it 5. And the last element, 329. So 9, the rightmost digit, we go to index 9 of our C array, which is 6. So 329 goes right over there. So we can definitely see that we have it sorted by our rightmost digit. We have 720, so we have them all sorted because we have 0. So maybe go ahead and sort of write this out. We have a 0 here, 5, 6, 7, 7, 9, 9. So it's definitely sorted. And we can see here once again, 839 was further to the right than 329. So we still preserve that same order over here. And same idea for 657 and 457. So 657 appeared to the right originally, and it still appears to the right in this sorted array. So we can definitely see that it all worked out just fine. So we sorted it correctly by the rightmost digit. So that was our first pass of Radix Sort. So I'll put this here. That was our first pass. So in this case, we have 3 digits for all these numbers. You have to do 3 passes of counting sort. Let's go ahead and let's finish the example up. I suppose since we already began, you might as well finish it. So I'm going to, I think I can copy this A array. I'll probably copy both of these actually, to just speed things up a little bit. I think this will work. Okay, that's good. That's okay. That still works out just fine. Okay, so I'm going to go ahead and rewrite this A array. So we're going to copy everything from that B into this A array, and then we're going to do the same process again. So let's go ahead and erase all of these. Now we'll set these all. This, so it's right. Definitely faster in writing the entire thing out again. Well, it seems faster. At least it seems less stuff to write, I guess. All right. So now we're going to go ahead and copy these over. So 720, 355, 436, 457, 657, 329, and 839, like that. So again, we're going to create our C array because now we have to sort them by that middle digit. So hopefully you can kind of see why a stable sort is needed, but I'll do an example of where if you don't have a stable sort, it will mess up. But hopefully this kind of, you see right there why that's the case. But if you don't, then, we'll make it clear in a second. So now again, we're going to count how many digits we see. So the first element contains 2. So I'm actually going to first set these all to 0, just like we're supposed to for counting sort. Okay, so now we're going to use, okay, so 2, we go to index 2 of a C array, increment this by 1, so we've seen 1 digit 2 so far. Then next element over is a 5, so we increment this index 5 elements, you've seen a 5 so far. Then 3, we go to index 3 of our C array, we've seen 3 so far. And index, so value 5 is next, index 5 of C, we increment this by 1, so you've seen 2 5 digits so far. Then this number here, so 657 has a 5 for its middle digit, so we increment that by 1 again, so you've seen 3 5s. Then 329 has a 2, increment this by 1 to make that 2. And 839 has a value 3, go to index 3, increment this by 1. So it was 2, it was 1 before, I believe, right? Okay, so let's make this 2, and that should be 7 elements. So yeah, 2 plus 2, okay, cool. So there we go. So we first counted how many digits we've seen for each middle number. So now we have to do that same exact process. We have to first go ahead and just so we have, we have to add elements over. So we have 0, 0, we're gonna add a 4, so we're gonna have 2 plus so we had 2 over here. So plus the previous one was 2, so we're gonna have 4 over here now. Then we copy the 4 plus 0 to make it 4. 4 plus 3 makes that 7. 7 plus 0 will be 7. 7 plus 0, also 7. 7 plus 0 is 7, and so forth. So now we can go ahead and easily map the elements from a array into a final sorted array. Let's go ahead and do that just next. So I'm going to copy this. I have to redraw all of that. Awesome. This will be our B array, that final product sorted array. So I clear all these out. And let's go ahead and work this example out. So going from right to left, we have 839, index that value is, that digit will be 3 for middle value. So index 3 of the C array contains 4. So go to index 4 of the B array and write 839 right there, and decrement this by 1. So now it's going to be 3. So if you see a 3 again, it will go to index 3 from now on, which does make sense. And now we have the next digit, or next number over to the left, we have next 329. It contains 2 for its middle digit. So index 2 of our C array contains 2. So 329 goes into index 2 in our B array. And we're going to decrement this by 1, like that. And then we're going to continue. So now we have 657. It contains 5 for middle digit. So index 5 of our C array contains 7. So we're going to write 657 right over there and decrement this by 1. So if we see a 5 again, it will go to the left of 657. And then let's see what else, where we at? We're at this one. So 457 comes next. So this number contains 5 for its middle digit. So we'll go to index 5 of our C array contains 6. We put 457 right there and decrement this by 1 again. And moving along, we now have 436, which has 3 for its middle digit. Index 3 of the C array contains 3, so you put 436 right over there. And we're going to decrement this by 1, so next time we see a 3 again, it would go to index 2 potentially. And now we have the next element over to the left is 355. So the middle digit will be 5 in this case. So index 5 of the C array contains 5. So you write 355 right over there. and decrement this 5 by 1. And then the last number at the end, we have 720, which contains 2 for its middle digit. Index 2 in C array contains 1, so 720 goes right over here. Oops. And we decrement this by 1, which will be the result of our second pass. Let me see if I got my notes, if I get that correct. I think it should be correct. Yeah, those look correct to me. So it looks like we have everything sorted properly. So if we look at this, we have a 2, 2, 3, 3, 5, 5, 5. But notice now, we have 20. So we have 2, 0 and 2, 9. So we can see here that we have everything sorted by not just by this middle digit, but by this entire numbers are sorted. The leftmost digit is not really sorted quite yet, but we can see here that it's actually sorted by these 2 digits to the right of that leftmost digit. We can see that, and that's why we want to have a what's it called, a stable sorting algorithm, because otherwise this order might not be preserved. So we have everything sorted correctly, except we don't have it sorted by the leftmost digit just yet. That's sort of, the idea here. We want to have it like this. So we can already see right now that having a stable sort is sort of important for Radix sort, or else, because what could happen is, for example, we have this 2 over here, and we have this 2 over there. So if we sort it by that digit 2, then really maybe that 29, so this 329 could go in front of 720, possibly, because for a non-stable sort, these 2 2s doesn't really matter which order they go in. I mean, it doesn't matter really, because if you're looking only at that 2 digit, who cares which 2 is first or second? But for this algorithm, it does matter, because if it's not stable, this is going to cause some issues. So this is going to be our second pass. Of Radix Sort. So let me see, I have 207, so not much time left. So I don't want to really begin the third pass and kind of halfway, stop it. So I'll continue this next time. So we'll do a third pass next time. We'll finish this example up, and I'll go over some runtime analysis and go over in more detail why a stable sorting has to be used for Radix Sort. But I guess for right now, I'm going to go ahead and just sort of stop class right here. If you have any questions, I'll stick around, but I guess sort of take care for right now. Stay safe. Thanks for watching, and I'll see you guys next time.